Hello, class. This is the fourth lecture that I'm giving today, and the last one, that is for sure. But I think it's also the last in the series of heavy mathematics derivations and you understanding the math and seeing where the various different things come from when we start talking about, real engineering, because that's what we're doing. We're going to start to get into the practical application of the propagation constant and the telegrapher's equations, which I think go back to the early to mid 1800s, or maybe, I don't know. There's a lot that we can talk about too. In the change. When we went to the telephone could not use the same telegraphic network that the telegraph used. Mainly because in so many ways the telegraph was a digital, on off type thing. But maybe I'll talk about that a little bit later on. Right now, we're still talking about some heavy duty equations here. And so the last thing that I really have to look at is characteristic impedance. Characteristic impedance of the transmission line. And this is not, remember, impedance is not resistance, is it? No. Impedance is resistance plus J reactance, right? So, wow, that is bright. But whatever. I wanted to do this lecture sort of right after the last lecture because I'm using some of the same equations out of the telegrapher's equation to derive the equation for characteristic impedance. And I'm not just going to give you, characteristic impedances. I remember my first electromagnetics course. It was, well, yeah, here it is. It's just a square root of L over C. That's what it is, and that's what it is. Just don't ask any questions. And I thought, well, how did you get that? And of course, that's not what it is anyway, right? That's what the approximation can be if you make certain assumptions, but that's not what it is. So what I want to do is I want to take this from our last equation, and I want to look at our equation. Before, in that last equation, you remember I was referring to V of Z. Well, what is V of Z? Well, V of Z is going to be some V0, some V magnitude, some V peak, whatever you want to call it. I'm going to call it V sub 0. And then E to the minus gamma Z, right? Because gamma is our propagation constant. So that's what it is. And if I wanted to take V of Z with respect to Z, in fact, is that a partial? I don't know. I wouldn't really say that is a partial, is it? That's not really a partial. It's more just it. Anyway, I get V0, right? Let's just do it. And then E to the minus lambda gamma Z. And then let's take the derivative of minus gamma Z with respect to Z. And that's just going to be minus gamma, isn't it? So I've got V sub 0 times minus gamma times E to the minus gamma Z. Does everyone see how that worked out? I'm sure everyone's fine with the derivation that I did there. So anyway, I wanted to do this because I'm going to use it in just a second. But let's go back, and I'm going to just encircle these. Because, excuse me, fourth lecture of the day, I want to write down the two Telegrapher's equations, right? Can't get enough of those telegrapher's equations, can we? Now, what I'm going to do is I'm going to take the negative sign that I used before on the left-hand side of the equation. I'm going to stick it over here on the right-hand side of the equation. That's all I'm doing. It's still going to be r plus j omega L, right, times I sub z bar. You know, I could rearrange that somewhat, and I could write it, let me just put a line down here, and I could say that I sub z bar equals the partial derivative of v with respect to z, right? You see what I'm doing there? Times 1 over minus r plus j omega L. Does everyone see what I did there? I just took that minus j omega, or minus r plus j omega L here. I just brought it over into the denominator on the other side, and that, of course, kept that there, and then I switched it all around and everything. So I think everybody can see what I did. Should be no problem. So I've just switched that around a little bit, but what I want to do is I want to write my other telegrapher's equation. So let's say, now was this the first or the second telegrapher's? That was the first telegrapher's equation. And my second telegrapher's equation is the partial of z, of I bar sub z with respect to z is going to be equal to minus, and again, I just took the minus from the left side to the right side, just like I did in the other one, times v bar sub z, right? And so that is my second telegrapher's equation that we just, of course, spoke about in the last lecture, which was on the telegrapher's equations. And that's why I'm doing the characteristic impedance derivation right after that, because you're familiar with all of these symbols that I'm using. Now, what I want to do is I want to take these things that I've got here, and I want to write an equation for I bar sub z, right? We've already got it up here. So it's the partial derivative with respect to z, and that's in the numerator. So partial derivative of v with respect to z. Where have I seen that before? Oh, right there, haven't I? So partial derivative of z of the thing with respect to z right there. So I have v sub 0. Yeah, I'm just looking at v sub 0 times minus gamma times e to the minus gamma z in the numerator, and I have minus r plus j omega L in the denominator, right? Now, let's expand that out a little bit. I still have v sub 0 e to the minus gamma z. Where have I seen that before? Oh my God, that is v of z, isn't it? So this right here is v of z. I think everybody can see that, right? And then let's expand out minus gamma. So I've got minus the square root of r plus j omega L times g plus j omega c. Everybody remembers in the last lecture how I derived gamma, I think, right? So it's no problem. And then e to the, oh wait, no, I've already put e in there. Where's my, there you go. Ooh, caught that one fast. That's the fourth lecture of the day, correct type. I'm losing it. All right, so, and that is all divided by minus r plus j omega L. And I think I see, everybody sees what you got here. I've got the square root up there. So this is really, if I wanted to take that square root and bring that square root down here, that would be that squared, wouldn't it? And then that would cancel out with one of those. And the minuses would both cancel out, so I don't have to worry about those. And so what I get is I get I sub z bar equals, wait a second, where the hell am I? V of z yeah, v of z times the square root of g plus j omega c over r plus j omega L, right? Does everyone see that? I'll bring that down a little further. Now, if we're looking for the characteristic impedance, what I want is I want V of Z over I bar of Z, right? And what that would give me then is the square root of R plus J omega L over G plus J omega C. And I'm just going to write Z sub 0 there. And I'm going to put a big, now you see why it's not L divided by C? That's right. What was he talking about? I'll tell you what he was talking about in just a second, but now look at that. Now, that's my characteristic impedance. And we also have up here my, I'll just put it here, my propagation constant. And my propagation constant is R plus J omega L times G, and these are primes, of course, prime plus J omega C, right? And all these are primes because we're working with them per unit meter. It's just that it's much easier to write all the primes in right at the end. So there's my disclaimer, 1, 2, 3, 4. There's no primes up there, but all these are primes. So, and why don't we, because I love to draw it, draw the communication circuit, right? And of course, this would be my ground, and this would be my signal, and G is always, everything that we're going to do in this class is always going to be 0, but not R. R prime will not always be 0. So there's my communication circuit, and that's what we're really going to be looking at now for the next maybe five lectures or something like that, in a whole variety of different ways. Now, and I can sort of preview where we're going. Let me just say this first. The propagation constant is the attenuation constant, that's the real part, plus J times the phase shift constant. Let's write that down. Alpha equals attenuation constant beta equals phase shift constant. All right. What are they in? Oh, okay. Alpha is in Neppers. This is, yes, this is the engineering unit. That's how it works out. You know, it's just like we don't use degrees. We use radians, right? Because that's the real thing. Well, that's what a nepper is. The nepper is the real thing compared to a decibel. So you've got neppers per meter. Now, what is a nepper compared to a decibel? I mean, nepper is a unit of attenuation, isn't it? It's a unit of attenuation. So a nepper, you can look it up. Yep, a nepper is minus 8.68 decibels. And you should, and I'll talk a little bit about decibels too. I can't imagine that you guys don't know decibels like the back of your hands, but I'll talk a little bit about decibels. But a nepper is minus 8.68 decibels is what it comes out to. And that's what you're going to get when you do the math right and all of this. And then when you look at the phase shift constant, that's going to be in radians per meter. And by radians per meter, I mean radians of expansion of the wavelength per meter. So the further you go, the further phase shift there's going to be relative to the original signal. All right, so that's a loss. There's a loss along the way. And anyway, we'll get into that a lot more because let's face it, this right here is a complex number. It's a complex number, so we're working with complex numbers now as to what the propagation constant is. And by finding the attenuation constant, we can tell what the decibel fall off is for any metallic conductor transmission line, whether it's transmitting power or whether it's transmitting signal. You know, if it's a Cat5, if it's a coax, if it's a microwave horn, whatever it is, we can figure it out now because we're going to find out the propagation constants here and stuff, right? And once we find the propagation constants, and we can use this. Now, why did an instructor of mine a long time say L over C, L prime over C prime? Now, there is a low, what's called a low loss approximation. And that's a low loss approximation to both, of course, the characteristic impedance as well as the propagation constant. And the low loss approximation states that R prime equals 0 ohms per meter and G prime equals 0 mhos per meter. All right? That's what it says. And if you do that and you look at the equations, well, if that's 0 and that's 0, then I've got J omega L divided by J omega C, and the J omegas cancel out, so I've just got L over C, the square root of L over C, right? Does everybody see that? And so that's where, with the low loss approximation, if you make that approximation, Z0 becomes the square root of L over C, okay? And what happens to the propagation constant? Right? The propagation constant is now the square root. Let's look at it. Where is that propagation? Here it is. The square root of 0 plus J omega L, right? That's a J. Times G, which of course is a 0, times J omega C, right? Now, let's do that. I've got J squared omega squared LC. So if I take the square root of that, that gives me J omega times the square root of LC. Does everyone see that? Now, if that equals my real attenuation constant plus my imaginary phase shift constant, which one is it? Right? There's a J in front of it. It's a J. It's a J. So what this tells us is that alpha equals 0 neppers per meter. So when we make this low loss approximation where the actual resistance is equal to 0, this is pretty, realistic approximation. I mean, foamed polyethylene is a very good insulator, right? So there's not really a lot of voltage being transferred from the inner signal wire to the outer ground shield on the coax, is there? No. But this, we don't have a superconducting conductor as the ground shield and as the signal line. So if we don't, then this is not real, is it? I mean, if this if this were real and we had a superconducting and there was no loss whatsoever, no resistance per unit length, then we could make this approximation, and of course we could send unlimited high frequency stuff over that all the time and never have a problem. It doesn't exist. It doesn't exist. There's the problem. Right? Because that is J, and that is J, and there's nothing without a J in front of it. So we know, and I want you to always remember that too, because I'll probably give you a question on a test that just sort of asks you that conceptual knowledge. So that I understand that you've seen this lecture and you understand that conceptual knowledge. Now what we're going to do, God, I'm losing my voice. That's no good because I want to do 4 more lectures tomorrow. Now what we're going to do, look at that. That's not even going out of focus too much, is it? I want to start applying these. All right, let's see how we apply these and then see how we now get attenuation graphs of how transmission lines are attenuating along the length of the transmission line due to us figuring out what the resistance per unit length, inductance per unit length. We're not even worrying about that, that's 0, and capacitance per unit length. Capacitance plays a bigger role than you know. And later on, if I do take some time to talk about some communication theory, which I also teach, maybe we could go into that, but probably not. I've lost my voice. That's the end of the 4th lecture, and who knows if I'll even do one tomorrow. See you guys later.